Virtual particles? What kind of nonsense is that?
What do you mean, virtual particles? I think that's pretty much how many people react when they first hear about them. And it's understandable. One of the main definitions of the word virtual is not physically existing. Okay. But then we're told that these very virtual particles supposedly have quite real effects. That's where it gets tough. How can something that doesn't exist exert influence on the physical universe? Something is clearly off here. Either it's just the choice of the word virtual to name these particles, or it's our understanding of all this, or even the way scientists describe reality. And it's a bit of everything. If you read articles about virtual particles, you can sometimes come across very different, even opposing claims. Some write that they don't actually exist, while others say they are quite real. And indeed, even scientists are still debating this. So let's try to sort all this out. What are virtual particles? Where do we encounter them? And what are they used for? Where did this concept even come from? What arguments are there both in favor of their existence and against it? I'm Andrei, and this is Cosmos Elementary. The topic of virtual particles is quite confusing, and how could it be otherwise? After all, here we're dealing with weird quantum stuff. I've mentioned virtual particles more than once, and we've encountered them in all sorts of topics, from black holes to the fundamental properties of the universe. But I've never really paused to focus on the particles themselves in detail. Well, it's time to fix that. It does sound extremely strange. Some kind of virtual particles, yet they seem to have quite real effects. Alongside all the invisible dark matter and mysterious dark energy, it's easy to see why some laypeople feel a certain skepticism toward modern physics. It also doesn't help that some popular explanations sometimes simplify things too much, that the explanation ends up being simply incorrect and misleading. And today I'll give some examples of this, although of course we can't do entirely without simplifications. First of all, it should be said that the concept of virtual particles is used in quantum field theory, the modern theory of elementary particle physics, and it is also applied in other areas. QFT is one of the most successful modern theories. Successful in the sense that it does a fine job of describing many phenomena and makes predictions that are confirmed experimentally. As I've said before, the particles in quantum field theory are not really particles, or at least not tiny little balls or tiny chunks of matter the way we're used to imagining them. Instead, the picture is completely different. The entire universe, at every point in space-time, is permeated by fields. By fields, we mean something that extends throughout the entire universe, has a certain value at every point in space, and that value can change over time. Fields can be scalar, meaning the value at each point of the field is described by just a single number. For example, with the help of a scalar field, one can describe, say, the temperature in the room and how it varies over time. You can measure the temperature at every point and create a three-dimensional map. In vector fields, a direction is added as well. With their help, one can describe, for example, the movement of wind. So in quantum field theory, particles are excitations in the corresponding fields, not little balls. An electron is an excitation in the electron field, a quark in the quark field, and so on. A field can have a minimum possible energy, and when in a certain region the field is in that state, there is nothing there that we would normally call a particle. However, if in some region of the field there is a disturbance or energy, then that disturbance or oscillation is what we call a particle. And so every point in spacetime is pierced by all possible fields. They change over time, oscillate, interact with each other, and out of all this, everything we see around us is built. And one of the most frequent mentions of virtual particles is precisely connected with these fields, and also with the so-called vacuum energy. A simple way of looking at it is this. If there is energy in some field at a point in space, then there is a particle. If there is no energy, then there is no particle. But here we're dealing with the quantum world, and as we know, it's weird. It would seem that if we completely removed energy from all fields, in some region, we'd have absolute emptiness. But Heisenberg's uncertainty principle dictates that this can never be done entirely. Even in the lowest possible energy state, the fields still fluctuate slightly, and this is what's called quantum fluctuations. And this is our first encounter with virtual particles today. It is quite possible you've heard before that these quantum fluctuations are described as a kind of soup of virtual particles constantly popping in and out of existence. They appear in pairs, particle and antiparticle, and very quickly annihilate. All of this happens so fast and on such tiny scales that it's impossible to catch these particles directly. However, there are real, measurable effects that are supposedly explained by these quantum fluctuations and virtual particles. The first such effect was the Lamb shift, measured back in 1940s. In short, it had been predicted that the electron in the hydrogen atom should have the same energy at the 2s and 2p levels. But the experiment by Lamb and Rutherford showed that these energies differ, and this difference was called the Lamb shift. And Hans Bethe explained this shift by saying that the energies differ because the electron interacted with those very quantum fluctuations, or virtual particles. A more famous example is, of course, the Casimir effect. The essence of it is that if fields are everywhere, and at smaller scales they constantly fluctuate, then virtual particles or waves arise. In the case of electromagnetic fields, these would be virtual photons. These photons must have all possible wavelengths, and one can try to create conditions in which part of the photons or waves are restricted. For this, we place uncharged mirror plates very close to each other in a vacuum. Then, waves with a wavelength longer than the distance between the plates won't fit between them, which means virtual photons with longer wavelengths won't appear there. A difference in pressure should arise between the plates and the outside, causing the plates to attract each other. And indeed, they do attract, as was experimentally proven. Surely, some of you, when you hear about virtual particles, immediately think of black holes, because these particles appear in the most popular explanation of Hawking radiation, or how black holes evaporate. All that thing about virtual particles arising in particle-antiparticle pairs and almost immediately annihilating, but at the event horizon of a black hole, they can end up separated by that horizon, and so one particle escapes, and in this way the black hole loses mass. I already said that not everyone likes this explanation, and moreover, some even call it simply incorrect. But we'll come back to this later today. Another mention of virtual particles can be found in modern descriptions of the structure of particles, for example, protons. In addition to quarks, pairs of virtual particles are also included. Recently, I made a video about fundamental interactions, and there I said that for 3 out of 4 interactions, the carrier particles are known today. That's how these interactions are described. Real particles exchanging virtual particles. For example, 2 electrons exchange a virtual photon. Of course, these are not all the examples, but even from what I've already described, a fair question should arise. How can everything I've talked about be explained by something that doesn't exist? While I was searching for and reading information about virtual particles, I came across claims that they are real, that they must exist, but we simply cannot observe them directly, and also claims that they are not real at all, and are merely a mathematical tool. So, whom should one believe? In fact, there is no need to believe anyone. You can simply look at what arguments exist. As for the tools of calculation, I've heard people say that quantum physics is complicated. Sure, let's suppose we have 2 particles, say flying toward each other, and they are supposed to interact. How do we describe that? If we look at particles in the old-fashioned way, just as 2 tiny balls, the problem doesn't seem very complicated. But once you take quantum stuff into account, everything immediately becomes much more complicated. And particles are not just little tiny balls, as I said, but disturbances in field. And because of uncertainty, the more precisely we know one property of a particle in a given pair, for example, where the particle is located, the less precisely we know another, such as its velocity. For example, let me remind you that a more accurate picture of an atom is shown in the illustration on the right. Here, the electron is not depicted as a little ball on an orbit, but as an electron cloud, in which we can only speak of a certain probability of where exactly the electron might be located. And in order to describe the interaction of particles at the quantum level, very complex calculations are required. However, one can somewhat simplify the problem by using, for example, perturbation theory. The point is that if we have a very complex process, we can try to break it down into simpler components and solve those, and in the end obtain an answer that may not be 100% exact, but is close enough to satisfy us. In quantum field theory, though not exclusively there, the famous Feynman diagrams are used in a similar way. You've surely seen those before. They are a mathematical tool and a graphical representation of the interactions of subatomic particles. Here is an example of a diagram that depicts the interaction of two electrons. These diagrams are two-dimensional, and along one axis we usually have time, while along the other we have space. In this particular example, time is shown on the horizontal axis, although it is also often placed vertically. The solid lines represent the electrons approaching each other. And what happens when particles have the same charge? They should repel. That is exactly what we see in the diagram. After approaching each other, they fly apart in different directions. But what exactly caused them to scatter in opposite directions? That is indicated here. They exchanged a photon. And what kind of photon was that? Exactly, a virtual one. This diagram helps us intuitively grasp what is happening. Yet, it is not a literal illustration of how the two particles actually interacted. As we remember, at the quantum level, everything is not that simple, with all sorts of uncertainties and probabilities. In fact, there is an enormous number of possible variations of what happened in this interaction. The exchange of a virtual particle can occur in different ways. It may not just be a single one, and so on. And for each such variant, one can draw a diagram. Moreover, there may be ones in which particles behave quite strangely, for example, flying into the past. But some of the variants are more and some are less probable. And it's also important to understand that it's not just the image. Each diagram corresponds to its own equation, which can actually be solved. And even though the number of possible variants is enormous, it is not necessary to solve them all. It may be enough to consider just a few of the most probable ones. And when scientists solve the equations in this way, they can make certain predictions about what effects will arise. And these can be tested in experiments. We can also make predictions in this way in quantum field theory, and again, they are confirmed experimentally. And as we can see, virtual particles are an integral part of these diagrams and calculations. And it turns out that calculations involving virtual particles are confirmed, among other things, experimentally. So, do virtual particles actually exist? Not necessarily. At the very least, we have never directly detected the particles themselves. And given the small scales and short time intervals at which they should appear and disappear, it's not certain that we'll be able to find them. And the fact that calculations involving them work quite well does not by itself mean that they must exist. This is precisely what is meant by the statement that virtual particles are merely a tool for calculations. Here's what astrophysicist and science communicator Ethan Siegel writes about this in his article on virtual particles. Quote, "The calculational tool of virtual particles in the vacuum allows us to make quantitative predictions about how matter and energy behave as they pass through empty space, and how empty space comes to possess different properties when external fields or boundary conditions are applied. The particles, however, are not real, in the sense that we cannot collide or interact with them. No one doubts the existence of electrons. We can, for example, create a beam of them and build a television based on that. But with virtual particles, it's different. Moreover, in calculations, they can acquire quite strange properties. Virtual counterparts of familiar particles can have different parameters, and may even move faster than light, which clearly does not argue in favor of their reality. So what about those effects I described earlier for which virtual particles are used in explanations? Well, as for Hawking radiation, first of all, we haven't observed it directly, and we're unlikely to be able to. It's a theoretical construct, although one that is quite well motivated. But the problem is that this whole story about pairs of virtual particles arising at the event horizon seems to be simply wrong. What makes it even more confusing is that Stephen Hawking himself used this explanation in his popular science book A Brief History of Time. And it's no surprise, since the author of the theory himself explained the process this way in his book, that explanation spread and now is used almost everywhere. But in his scientific paper, he described it quite differently. And it's not about virtual particles, but about the curvature of space and reference frames. We won't dig into the details right now here. I'll make a separate video about that, so subscribe not to miss it. But the main point is that in popular explanations they are given the central role, whereas in the actual explanation it's really not about them. As for the lamp shift and Casimir effect, the effects themselves are measurable and experimentally confirmed. But again, the same logic applies here. These effects are described using mathematics that employs virtual particles. But it doesn't mean everything literally happens that way. The existence of virtual particles is not proven by these effects themselves. Therefore, one can encounter unequivocal opinions and claims that virtual particles are merely a mathematical tool, and in fact, do not exist. But not everyone agrees with this. A physicist, Matt Strassler, writes somewhat differently about virtual particles in this article, and he examines their involvement in fundamental interactions. First of all, he writes that, as often happens, words confuse us quite a bit here. The very word virtual, and for example the phrase exchange of particles when describing particle interactions. In science, there are quite a few names that can be misleading in their own way. Black holes, which are not holes, planetary nebulae, which in fact have nothing to do with planets, though it's a relic of the past, and the name is still in use. Imaginary numbers, and so on. So it's something similar here. And by the way, questions about these formulations may start to arise even if you just think a little about the processes they describe. As for the exchange of virtual particles, let's return to the situation with two electrons. In the usual description, two electrons with the same negative charge repel each other when they exchange a virtual photon. Here, one can also see the logic of how this happens physically, as if the photon pushes the electron and they fly apart in different directions. But how should this work in the case of particles with opposite charges, say an electron and positron? After all, they don't repel but attract. How can the exchange of particles cause two particles to come closer together? It's unclear. Matt Strassler describes the whole situation a bit differently, using the example of electrons. First of all, we again describe them as perturbations or oscillations in the electron field. But fields do not exist separately from one another. Different fields can interact. And when two oscillations in the electron field, aka electrons, approach each other, due to their charge, they begin to interact with another field, the electromagnetic field, sometimes also called the photon field, because photons themselves are oscillations of this field. So when two electrons come close together, they create a disturbance in the electromagnetic field. Such disturbances can be of different kinds. The one created specifically by two electrons has a repulsive effect. However, if other particles come close together, say an electron and a positron, then the disturbance in the other field will be different, and it may already have another different effect, an attractive one. Of course, this is a very simplified, intuitive description, yet beneath it, there is also concrete mathematics. But if we have two electrons that created a disturbance in the photon field, then what is the disturbance in the photon field? A photon. So it turns out that when two electrons come close together, they created a photon, a virtual photon. In this version, exchange of photon already sounds incorrect. But still, Strassler writes that this disturbance in the electromagnetic field is not a real photon. At the very least, it differs greatly from an ordinary photon. For example, it may not move at the speed of light. But the main difference in this description between real particles and virtual ones is that real particles can be touched or seen. They exist independently. They existed before the interaction, and they will exist afterwards. Oh, unless they annihilate. And virtual particles do not exist here independently, but the disturbance in the electromagnetic field, which we call the virtual particle, exists only while two electrons are interacting. As soon as electrons fly apart, this disturbance disappears. From this also follows a more complex view of ordinary particles, which at certain moments may exist not just as oscillations in a single field, but as a combination of disturbances in several fields. And this applies not only to electrons but also to other particles. The situation with virtual particles is also compared to the famous double-slit experiment. In the part where we send particles, say electrons, one by one through the slits and perform measurements. We do not know through which of the two slits the next electron will pass, and where exactly it will appear on the detector. Here both alternatives are added together and squared. Through which slit the electron will pass we do not know, but the probability is expressed this way. And the analogy here is that when we describe possible interactions, say of two particles, which we illustrated with Feynman diagrams, there too everything is added together and squared. And just as it is difficult to call one of the probabilities in the double-slit experiment real by itself, here it makes more sense to speak of a superposition. In the case of virtual particles as well, the individual terms involving them are difficult to call real in themselves. This is referred to as the superposition argument. Greg Jagger, the author of this paper, disagrees with this. He is a proponent of the view that virtual particles are indeed real. For example, he offers the following argument. Someone might say that we cannot regard virtual particles as real because we have never directly observed them. But there are particles whose reality scientists do not doubt. Particles that are very important, and yet we also seem not to have seen them directly. And I'm speaking of quarks. It used to be thought that everything consists of atoms and that atoms are the smallest possible parts of matter. Then it was discovered that atoms consist of protons, neutrons, and electrons. And in the second half of the 20th century, it was said that this was not the end, and that protons and neutrons themselves are made up of even smaller parts, quarks. Today, the theory of quarks, and not only them, but also say gluons, describes observable properties well, and again makes successful predictions that are confirmed experimentally. But at the same time, we have never seen individual free quarks. This problem even has its own name, confinement. Well, the story of why scientists believe that quarks really do exist in itself is a long one, and probably worth discussing separately. There are many interesting aspects and experiments there, and I'm going to make a separate video on this topic. But the main thing is that in experiments we observe a number of effects that for now are best described by the quark model. Yet we have not seen quarks themselves separately. Doesn't that remind you of something? And the author of this paper compares the situation with virtual particles. He writes in his article that modern theories involving virtual particles have excellent predictive power. So they quite possibly can exist as disturbances in the corresponding fields, which we're simply unable to detect. The situation is somewhat similar with the famous Higgs boson, whose discovery scientists announced in 2012. The thing is that Higgs boson itself also cannot be seen directly. Here's a quote from CERN's website about its discovery. The Higgs boson almost immediately decays or transforms into other particles, so it is not possible to observe it directly. The particles from the boson's decay are the only traces that it leaves behind. These traces have to be detected and precisely measured by particle detectors. So scientists collided certain particles, and in those collisions new ones appeared, which then decayed. By measuring the decay products and comparing the results with theoretical predictions, the scientists were able to draw conclusions about what had decayed. There are of course many nuances, and a large amount of data and collisions are needed for the discovery to reach sufficient statistical significance. And by the way, this process of Higgs decay is also described using the very same Feynman diagrams, which, as I already mentioned earlier, in itself does not prove the reality of virtual particles. Debates of whether virtual particles can be considered real have been going on for decades. Clearly, we can say that they have not been observed directly, and it's not certain that they will ever be. On the other hand, in science there are quite a few phenomena or objects whose existence we infer solely from indirect evidence. Sometimes indirect evidence is so compelling that even without direct observations, it is hard to doubt. And as we've seen, there are scientists who support the reality of virtual particles. Yet, after reviewing all the material while writing the script, I would say that most scientists still regard virtual particles as a mathematical abstraction, as a tool for calculation. This story also serves as a good illustration of how simplifications can confuse or even mislead. And as we can see, things here are noticeably more complex. Yet as particle detectors and accelerators continue to advance, something new may be discovered in this area as well, and the prevailing view among scientists could change. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more videos in future. Bye.